All right. Hello, everybody. Today we're going to talk about types of reactions. There are 5 types of reactions that you're going to need to know. So we'll go ahead and get started. This shouldn't take us too long. This is an awesome video that shows some of the reactions in this super cool photography. We will watch it in class, or you can click on this in the notes themselves, but I'm not going to take time to watch it during your video. Moving on. All right, the types of reactions. They can be classified into 5 types. Each type has its own characteristics and patterns. Identifying the types of reactions will help you predict products. So if I say, what happens when you combine hydrogen gas with oxygen gas, you should be able to look at that and figure out what the product is. And by naming the type of reaction, it's going to help you do that. So these are the 5 types of reactions. Write these down. Number 1 is called a synthesis reaction. Synthesis reaction is taking basic chemicals like hydrogen and oxygen and creating more complex chemicals. They're sometimes called combination reactions, and I need you to know both terms as though they're synonymous. So I should be able to say, oh, it's a synthesis reaction, and next time I should be able to say, oh, there's a combination reaction, and you should know that they're the same thing. They typically require energy to put into the system to run. That means that they are endothermic. We're going to learn a little bit more about endothermic reactions when we talk about biology. It's because you're trying to build a more complex molecule, and it takes energy to build more complex molecules. In context of biology, we are incredibly complex biological molecules, a whole series of complex biological molecules. So we have to keep eating, or plants have to keep collecting sunlight in order to get that energy to build these complex molecules. So that's called endothermic, when energy is getting put into it. So this is what a synthesis or combination reaction looks like. It often has more reactants than products. So there's several reactants at the beginning before the arrow, and then there's just one product usually at the end. Often elements are combining to form compounds. So when I say an element, I mean like just copper or just hydrogen or just oxygen. So here's the example that I've been talking about. Hydrogen, just an element. Oxygen, just an element. Why is it H2 and O2, KJ? Right, diatomic molecules. Those are both diatomic molecules, so they're always going to be. Now it needs to be balanced. That reaction is not balanced, but that at least shows you what the reaction is. The next one is called the decomposition reactions, and they're the exact opposite of synthesis. So this is breaking down a more complex molecule, typically releases energy. So for example, when we eat sugar, when we eat what plants have made during photosynthesis, it took a lot of energy to build that sugar molecule. When we eat it, we break it apart, and that releases energy that we use then to build our other molecules. So here's an example of a decomposition reaction. We have copper and nitric acid. I had to think what that one was for a second. And it becomes more complex as we go. So typically there's more products than there are reactants. Remember, reactants are in front of the arrow. Products are what get produced, so they're after the arrow. Combustion reactions are next. Combust, for something to combust, it means fire. And we're going to specifically talk about a particular type of combustion reaction. It's a reaction of a chemical with oxygen gas. So oxygen has to be present, and it is a very exothermic reaction. So example, gasoline is a super good example of a combustion reaction. For the combustion of a hydrocarbon, which is what gasoline is, and we learned about hydrocarbons when we were naming organic molecules. Those were hydrocarbons that we were looking at. The products are always, this is what's so fun about the combustion reactions, always carbon dioxide and water. And oxygen must be present. So here's the example of gasoline burning in your engine. Notice that the products, very simply, carbon dioxide and water, and notice that oxygen is present. So if you see those things, doesn't matter if you know if there was a fire or if energy was released, you don't need to know that. Just as long as you see those products and that one reactant, you are good to go. Okay, the next one is called the single replacement reaction. This is where one element is substituted for another element in a compound. So it involves a pure element. When I say element, again, we're just talking about something all by itself. So like copper all by itself, or hydrogen all by itself, not combined with another element. So it involves a pure element and an aqueous solution, so a liquid. Produces a visible product. One product is not soluble, so you can see it. And they are typically very exothermic. Here's just an FYI for something coming up. Let me oops, nope, that was not what I meant to do. I was trying to get my picture out of the way. This is something we're going to be doing very soon. I'm screwing it all up. Sorry. This last thing says not all elements can replace all other elements in a reaction. So we're going to learn that some elements are more active than other elements, and some will replace elements and some will not. So sometimes the reaction will go forward and sometimes the reaction will not. And you'll be able to predict that and know whether a reaction will occur or not based on something we're going to learn coming up. All right, so here's our pattern and example. So the pattern here is you have an element plus a compound makes a new element with that compound. Let me get my picture out of the way yet again. There we go. So take a look at it carefully. Notice that in this diagram we have, or in this reaction, we have aluminum all by itself, and then we have a compound. When the reaction occurs, the aluminum and compound swap places. Now, the tricky part on this is that notice that it is CuCl2 the first time, and the second time it's AlCl3. So the number of chlorines in the compound changes, and that's just a factor of crossing charges. The copper in this case would have been a +2, and the aluminum is a +3, and the chlorine is a -1. So when we cross those charges, we still have to make sure that molecule is neutral. It doesn't get to have a charge unless we specifically say it has a charge. All right, and then this is the last type. These are called double replacement reactions. It's when two ionic compounds trade their cations. So they're positive ions. They just swap places. Super easy to identify. It's the largest category of reactions. Yeah, and two solutions act as the reactants, and it includes acid-base reactions, which we will talk about later, not yet. If a precipitate is formed, so that's a solid that shows up in the liquid as one of the products, the reaction is considered exothermic. So let's take a look at an example. We're going to have a compound, and a compound forms well, that doesn't look like any reaction occurred. It's two new compounds that form underneath it. So they will have traded their cations. So take a look at this one. I wish I could get me out of the way here. There we go. So look at the NaOH and the CuNO3. So look at the Na, that's the cation, and the Cu, that's the cation. Now look after the arrow. They switched places. So notice how the Cu and the Na have traded places. And then we still have to cross the charges and balance them, but they've traded places. All right, cuties, that is it for this set of notes. Just make sure you're able to recognize all the different reactions, and then we'll look into predicting what's going to happen in those reactions. Have a great day.